Hello all, and welcome to the next video in our Introduction to X-ray Diffraction series. This is Chapter 2, Part 3, and it covers lattice directions. Now before we begin, I simply ask you to check the pinned comment below, as that is where I will add any information that I might have forgotten to mention during the original filming of this video. So let's just jump right in. We will look at a simple cubic unit cell. Down here, we have the crystallographic axes that I've chosen. X points this way, Y this way, Z this way. Now these were just my preference. You could choose them differently, so don't get too hung up on that. I'm going to make my origin down here. And then we are going to search for the UVWs, which are coordinates of points, and are unitless. So it's important to keep in mind that U corresponds to how far we're moving in the X direction, V corresponds to movement in the Y direction, and then W corresponds to movement in the Z direction. So let's just jump right in and take a direction here and figure out how to name it. So this direction begins at the origin and then travels one atomic spacing in the X direction, which makes our U coordinate 1, and then we don't really need to move at all in Y or Z, so each of those coordinates is 0. So we have the 1, 0, 0 direction, and directions we write in these brackets. We do have a couple of checks that we need to take care of. Are all of these integers? They are. Are they all the smallest common integers? They are. So then this is the 1, 0, 0 direction. What happens though if we draw this same direction just shifted over one atomic spacing? Well, this might seem like it's a little trickier in terms of the UVW coordinates, but remember, I just chose this origin arbitrarily. If we wanted, we could just simply move that origin over to this atom, in which case all of the same steps that we previously went through still apply, which makes this the 1, 0, 0 direction, which makes sense because it's pointing parallel to the other one that we just did. So that's why you can't really get too hung up on the choice of origin. Let's bring the origin back to what I prefer it to be, and then look at this new direction. To get to the end of the direction, we have to move one atomic spacing in X, half in Y, and 0 in Z. So that gives us UVW coordinates of 1, 1/2, and 0. Are they all integers? Well, no, we have a fraction in there, so we need to multiply by 2 to get 2, 1, 0. Are these the smallest common integers? They are, so this is the 2, 1, 0 direction. Now it might seem a little weird to have a 2 in there, or any number really above 1, because we only have one atom distance in each of these directions. But if we take a look back at the unit cell behind this one, and then shift our origin back to this atom, draw an equivalent direction because they're both parallel. Well, now we see that we need to move 2 atom spacings in X, 1 in Y, and 0 in Z, which then gives us the 2, 1, 0 that we have in our direction name. So hopefully that helps clarify kind of how we get these larger than 1 values. Let's go back to a single unit cell and check out this direction. Here we need to move half in X, 1 in Y, half in Z. So that gives us these coordinates. They're obviously not all integers, so we need to multiply by 2 to get the 1, 2, 1. Are they the smallest common integers? They are, so this is the 1, 2, 1 direction. Now what happens if we have our origin up here and we are still looking at that same endpoint? Well, now we need to move half in X, 1 in Y, and -1/2 in Z. That gives us these coordinates that are not all integers, so we need to multiply by 2 to get 1, 2, minus 1. We don't phrase it that way though. Instead of saying 1, 2, minus 1, we say that it is the 1, 2, 1 bar. And we write the minus sign essentially above the number that is negative. So just to reiterate, this is 1, 2, 1 bar. Are they all the smallest common integers? They are. So it is the 1, 2, 1 bar direction. Now let's look at families of directions. So here again, we have our simple cubic unit cell. Here we have the 1, 0, 0, 0, 1, 0, 0, 0, 1 directions. And then we have the negatives of those. So a family of directions really corresponds to directions that are related by symmetry. So all of these directions are pretty much the same. They are only designated as they are on the screen because of how we chose our axes. If we were to take our y-axis here, and instead of having it be positive pointing to the right, we made it positive pointing to the left, well, in that case, this direction would then become the 0, 1, 0. This direction would become the 0, 1 bar 0. And really nothing would change. The distances are all the same. All the symmetry is the same. So that's what we mean by directions related by symmetry. So for a cubic lattice, the 1, 0, 0 family of directions, and we write that between these types of brackets, they correspond to the pretty much the entire combination set of 1, 1 and 2 zeros with that 1 at each position, and then the negative of that as well. Similarly, for the 1, 1, 0, it's every combination of positive and negative 1s where we have 2 1s and a single 0. So you can kind of look through all of these and see how that gets set up. Now, I'm not going to go into too much detail on lower symmetry lattices. I will just point out that if we made this into a tetragonal lattice, so now this distance equals this distance, but we made this distance longer, well, this direction is no longer the same as these directions. They're not really related by symmetry because this length is different. So as a result, if we looked at a tetragonal lattice and looked at the 1, 0, 0 family of directions, this is what it was for cubic, but because now that z direction is different from the x and y directions, anything with a 1 in the, essentially the w position, goes away. So then the 1, 0, 0 family of directions for a tetragonal lattice only includes the 1, 0, 0, 0, 1, 0, and then the negatives of that. For the 1, 1, 0 family of directions, once again, we take out anything that has a 1 in that final position. So then these 4 go away, and we only have these 4 that make up the 1, 1, 0 family of directions for the tetragonal lattice. Okay, so now moving on from families and just back to regular naming of individual lattice directions, let's look at a hexagonal unit cell. So I'm going to gray out everything just to make some of my next animations stand out a little bit more. So here we have this direction. We'll just call that A1. This we'll call A2. And they are equal distances as dictated by the hexagonal system. And then this last direction, C, is different from A1 and A2. And that makes up the hexagonal unit cell outlined in red. So just a bit of a reminder about hexagonal lattices. So we have 2 different ways of designating directions in a hexagonal lattice. Option 1 is using what I'll list as capital U, V, and W, or I might call them big U, V, and W. So let's just take this direction to illustrate. To get from the origin up to the atom that this direction is pointing towards, we need to go 1 in the x direction, 1 in the y direction, and 1 in the z direction, which corresponds to a UVW of 1, 1, and 1. Are they all integers? They are. Are they the smallest common integers? They are. So this is the 1, 1, 1 direction, written in the option 1 way. Option 2 is to have lowercase or little UVTW. So we can convert from option 1 to option 2. So option 1, once again, was just the 1, 1, 1. So little u equals 2 big U minus big V divided by 3, which is a third. Little v equals 2 big V minus u divided by 3, which is 1/3. Little t equals either the negative sum of little u and little v. It also equals the negative sum of big U plus big V all divided by 3. Either way, that's negative 2/3. And then little w equals big W, which equals 1. So then if we took U, V, T, and W and listed them out, that's what it would look like. Are they all integers? No. We have to multiply by 3 to get 1, 1, 2 bar 3. Are they the smallest integers? They are. So here we have essentially equivalent directions just written in 2 different methods. So in summary, when determining directions, we want to find the coordinates of the end of the vector. If any coordinate is a fraction, we need to multiply all coordinates by the smallest number possible to obtain only integers. We then need to double check to ensure that the integers are as small as possible. For example, the 110 instead of the 220. And then if we have any negative directions, they are written with essentially a minus sign above the number that is negative. And we say it as 1, 2 bar 1 in the example shown. Families of directions are all directions that are equivalent due to symmetry. Non-hexagonal lattices have 3 axes, whereas hexagonal can have a 4th. Then we have our 2 options that we went over for reporting directions in the hexagonal unit cell. And this is how we relate the two to each other. So that's pretty much it. As always, Gus and I thank you for watching, and we hope you have a great day.